Hello, everybody, and welcome to our last Origins seminar of the semester. Today's speaker, well, before I get to that, I would like to remind everyone to please hold your questions until the end, unless it's a clarifying question that just can't wait, and then you can put it in the chat. And I'd also like to remind you to turn your video off if you are not speaking so we can conserve bandwidth. But with that, I am pleased to introduce today's speaker, Carlo Manara. Carlo got his PhD in Munich with Leonardo and Barbara Ericolano, and he is now a support astronomer at ESO in Garching, and in addition to supporting all the wonderful telescopes such as you see here, he's also an expert on protoplanetary disks, and he's going to be telling us about some of his work today. Carlo, the floor is yours.
Hi, thank you very much. I'm very happy to be talking also to a slightly different audience to the one I usually give talks to. I'm very happy for this opportunity given by Zoom and everything to be ready to talk at your university. So today I will present some of the work I've been doing in the past period. And this is work done with many collaborators. I want to quote in particular two master's students, Alessia Rota and Giulia Bettoni, who have been working on quite a big fraction of what I will present today. So Alessia is now going to start a PhD in Leiden with Nienke van der Marel starting in October, and Giulio here in Garching with Wine van Dijok. So today, the topic of what I want to present today is based on the fact that if we want to understand how planets form in protoplanetary disks, we have to consider the fact that many disks are actually born in environments that are quite different to what we usually see in our neighborhood. These are environments where there are many stars, and this implies that the disks where planets form will evolve with a strong imprint from their surrounding. And in particular, there are two effects that happen in these kind of environments. There is the truncation due to dynamical interaction in multiple stellar systems or in dense environments where you have flybys of other stars, and the photoevaporation, the external photoevaporation induced by massive stars that are nearby your protoplanetary disks. Both processes have, in short, a very similar effect on the disk. They will remove mass from the outer part of the disk, shrink the disk to small size, and cause a rapid dispersal of the disk. So when we look at our classical picture of how protoplanetary disks evolve, and we have our nice evolution of classes and a nice decrease of the fraction of disks in a given star forming region with age, we can ask ourselves whether this kind of evolution happens similarly for single stars or for disks in more denser environments or in multiple stellar systems. And what we know is indeed that if you have multiple stellar systems, what will happen is that the disk will be truncated. So this is something that depends on many parameters, depends on the individual orbit of the disk, and depends on the mass ratio of the binary, and on the eccentricity of the orbit, and on many parameters. But in short, what you expect is that typically you will have a truncation to a third of the separation of the binary. And if you try to study what happens on the evolution on the plot that we have seen before of the fraction of stars with optically thick disk as a function of the age of the region, you can try and see whether there is a difference for binaries. And I didn't find many work in the literature about this, and please, if you know more, please let me know. But I was quite intrigued by this work of Sebastian Demgen quite some years ago, where they actually showed that the disk fraction is smaller in binaries rather than in singles, and this might imply a faster evolution of these objects. And if you ask yourself whether the evolution of disks is faster around multiple stellar systems, you can also ask yourself whether on these shorter timescales, you will actually be able to form planets or not. And what we know actually from surveys of exoplanets is that you actually form planets around multiple stellar systems. There are not many planets detected in multiple stellar systems, but there are already hundreds or more of them. And this is definitely something, the low number is partly also due to clear biases in the surveys for planets that actually usually try to target these planets around single stars, but it might also be intrinsic. It might be more difficult to form planets around stars in multiple systems. This is really then a question of how can we understand from the other side, so from the side of planet formation, whether planet formation is possible at all around these kind of systems, or how can you form planets in these multiple stellar systems. And there is also another quite intriguing recent result that got my attention, which is this work done by Andrew Winter and colleagues that was published recently on Nature. And what they looked at is what is the density, the stellar density of stars that are hosting planets. So this is something that we have to take, of course, with a little bit of grain of salt if we want to put it together in the context of the formation of planets. But it's very intriguing to see that the planets, the stars that are located in higher density regions, so that are shown here on the right-hand side, they actually have a higher fraction of hot Jupiters around them, which is a very intriguing result in the way that it suggests that if you truncate the disk, you might actually impact how your planets form, and you might actually even trigger or enhance the possibility to form hot Jupiters. So this is, of course, a big leap that I took in putting this statement, but this is something that we have discussed in a workshop last year, and this is something that is really something we want to explore in the future. I will conclude my introduction with just what the mention that, of course, the way that we all know that how disks evolve in multiple systems is also that in some cases, these kind of multiple stellar systems are also interacting, and this leaves a big imprint on the properties, on the morphology of these disks and on the large scale morphology around them. So here I show just some examples that have been recently published in the literature that actually show really that when these binaries interact, you will see all kind of arcs and all kind of structures that are really due to these tidal interactions. This is not what I will talk today about. I will try to focus more on tidal truncation in non-interacting systems and how this changes the morphology of disks. And to do that, I will start from a survey that was carried out in the last years, led by Greg Herzeg. And this was the survey done with ALMA in the Taurus star forming region. So this survey was slightly different than other surveys that have been done recently, in the sense that it was targeting a small sample, but at high spatial resolution, so 0.1 arcsecond, and with a pretty deep sensitivity. And in this survey, there was no choice against disks with structures or in favor of disks with structures and on a stellar multiplicity. We only excluded the very close binaries, so with a distance of less than 0.5 arcsecond. So this resulted in actually a sample of very interesting disks with very different disk morphology, and also with a significant fraction of disks that are actually disks in multiple stellar systems, which are usually not interacting, although we will see that some of these are actually quite interactive. And this sample is what I started to study a few years ago to actually understand what are the properties really of disks in multiple stellar systems. So here I show just a gallery of the continuum images of these 10 systems that I've studied. And you can see that their morphology and also the relative inclination of the disks, etc., is very different from one system to another. And also the mass ratios and many other parameters were quite different. And what was interesting here is that we were able to detect and resolve both components of the binaries in many of these disks, which is something that that really represented a new step in our understanding of these objects. So what we actually did is to study to model these disks in the UV plane, and we did this using the tool, the Gallery tool, which allows us to represent with simple functional forms the disks around the 2 or 3 components of the multiple stellar systems we were looking at. The fit were actually carried out on all the objects, and similar fits were also carried out on the single disks in the surveys, so in the Taurus star-forming region. And one of the first results we obtained, which is already visible from the plot here in the bottom left, is that the disks around the single stars resulted in less truncated outer disks than the one in binary systems. So this was already a quite interesting result for us, although we are, of course, hitting the noise here, but it was already possible to start to show that the disks around multiple stellar system are really truncated in the outer edge. But the most interesting result, in my opinion, is the fact that the disks around multiple stellar systems are actually shown by this work to be really smaller in size than disks around single stars. And you can see it in the left plot, where we plot the luminosity of disks, of all the disks in the Taurus star-forming regions we studied, together also with the, I'm pretty sure it's the D-sharp disks, as a function of their 95% radius. So here, of course, when we study radii of disks, we have to define a metric. And for the majority of the plots that I'm going to show you, we actually looked at the radius where 95% of the flux is contained. And this is really to actually try and go to the real outer part of the disk, where actually where we can actually say this is the real size of the disks. And what you see here is that the more massive disks are also the larger, as we already knew, and they are all found around disks with clear substructures. There is then smooth disks in single systems, and clearly smaller the disks around binary systems. And this is also shown here on the right-hand side with a cumulative distribution. And we can actually conclude that the disks around single stellar systems are larger than those around multiple stellar systems. And also in multiple stellar systems, we see that disks around secondary stars are smaller than disks around primary stars. So this was already a quite interesting result for us. And we also wanted to see whether these sizes that we recovered were compatible with models of tidal truncations. So we started first with a pretty simple comparison. So putting the measured projected separation of the systems of the components of a multiple stellar system as a function of the radius of 95%. And we were quite surprised to find that most of these disks are actually way smaller than what we expected. So all these disks had sizes that were less than 0.1 the separation of the orbit. And this is definitely something that would not be expected from zero eccentricity models. And so unless you really have very high eccentricity, these results are not what we would have expected. But of course, here we were looking at dust radii, so dust sizes, and we know that the gas radii are larger. So in this first work, where we didn't have information on the gas component, we actually tried to see whether their models of tidal truncation were more compatible with our data, with a simple assumption that the gas radii are about 2 times larger than the dust radii. And this is shown here with this solid line in this plot that shows the predicted truncation radius as a function of the projected separation of the binary, where the prediction of the models is these black lines. And you can actually see that in these objects, for example, this is our W-Auriga, the result of this assumption is that our measurements are compatible with models expecting an eccentricity of 0.2, 0.3, which could be already compatible with what we expect, but is in any case in other system, this assumption of the gas radii being 2 times larger than the dust radii was not enough to actually reconcile our finding with typical models of tidal truncation. And this result has actually started some new analysis. From the theoretical point of view, there is a group composed by Francesco Zagaria, Giovanni Rosotti, and Giuseppe Lodato, who actually started to investigate what actually happens in the evolution of dust around in multiple stellar systems. And in particular, they actually coupled the evolution of a viscously evolving disk with dust evolution in the disk, and actually predicted or imposed an external truncation of the disk using the same models that we were testing before, and checked whether radial drift in these systems is faster or not than in single systems. And the conclusion they came to is really that radial drift is faster as soon as you tidally truncate the disk, which on the one hand could already explain some of the results of the work that I just presented, and I encourage you to stay tuned, because they are really soon publishing a paper where they are actually showing why the dust radii were so small. But they were also suggestive of the fact that in these multiple stellar systems, this ratio of the gas to dust radii would actually be larger than what we usually observe in a population of mostly single disk in nearby star forming region. And this is also partly the motivation for what we've actually done in the past year or so. What we have done is to actually collect new data with ALMA, targeting the same objects that we studied before in the continuum, and trying to observe them also in the gas. So we decided to actually observe these objects with slightly lower resolution than the one we used in the previous observations, but to go very deep. So to observe these objects for about 40 minutes per target, to really detect 12 CO down to when it's optically thick, and also other molecules. So we also targeted the other isotopologues of CO. We detected formaldehyde and other molecules in these disks. And we were very happy that our observations were successful. So we managed to detect all the primary stars quite clearly, and also many of the secondary stars in these systems. We also realized quite immediately that our data were showing that some of these systems are clearly interacting, as you see here for UIR and T-tau, where you see that it's actually a very complex systems where the A and B component of OIR are surrounded by all kind of structures that is now being studied. And we also decided, but we also realized that in many disks, we were actually able to really study their sizes, which was the main goal of our work. On top of our data, we also use the data from Rodriguez, who actually share with us their data to complete the sample that we had before. So here what I'm showing is the moment zero of the 12CO emission. And we also have some nice moment one maps where you actually see the different inclinations of the disks in some cases. So for example, the HK tau system, which was already well known in the literature. And you also see how complex the structure around YR and T tau is. And this is actually something that other colleagues at ESO are studying right now. And this is actually a very interesting system where we are seeing all kind of interaction between the components and probably also with the surroundings. But this is material for another talk. So with this data, we actually wanted to really test what is the size of disks in multiple stellar systems in their gas component. And we decided to proceed with a simple cumulative flux method to measure the radii, since other methods that we consider were not as easy to do as this simple cumulative flux that was actually leading to very robust results. So we recalculated the position angular inclination from the CO emission using the EDDI tool by Richard Teague. And we actually measured the 68% and the 95% radii for these disks. And these are shown on this plot, on this moment zero maps for all the objects in our sample. So this is, I'm pretty sure, the first time that there is a decent sample of multiple stellar systems for which we have both measurements of the gas and the dust radii. And this was for the first time we could try to see what happens in these systems, whether the ratio of the dust to gas radii is different than in single objects. And indeed, the result is that this ratio of gas to dust radii is typically larger than 2, and actually goes up to 4 or more in several objects. And this is already quite interesting, in my opinion, because it already shows that there is a difference when you look at systems that are experiencing tidal truncation. And if you compare this ratio of the gas to dust radii between the multiple stellar systems that we studied in the Taurus region with the recent results for the lupus star-forming regions by Enrique Sanchez, you actually see that there is really a difference in the typical gas to dust ratio in these objects. And very interesting to me is that this difference is present only when looking at the 95% radius rather than the 68% one. So the way I'm interpreting this is that this is again due to the fact that the dust radii are sharply truncated. And when you look at the 95% radius, you actually have significantly smaller dust radii than the gas radii. And this causes this very large difference in their sizes. So this is, to me, quite a strong result also that goes in the direction of the faster radial drift in multiple stellar systems that was predicted recently by the work of Zagaria. But it's also interesting to test at this point the tidal truncation models with real measurements of the gas radii, which are the ones that are truncated by the tidal truncation, by the tidal interactions. So this is what we have done. We have compared our measured gas radii with the models of tidal truncation, and you see on the left-hand side, again, the projected separation of the binaries, versus the measured gas radius for several objects and both components when possible. And you immediately see that the values that we obtained are much larger than the 0.1, and in many cases are closer to the typical 0.33, the ratio between the radius and the separation. This is, of course, a typical ratio, which you would expect for eccentricity equal 0. And the fact that this is not what we observe in many objects is actually simply suggesting that most of the orbits of the binaries that we observe are on higher eccentricity than 0. And we actually find in our work that for most of the objects, we could find a solution with an eccentricity of about 0.2, 0.5, which is quite in line with what we expect for typical multiple stellar systems. So with this new data, I think we can really conclude that we can see how the dust and gas evolves in multiple stellar systems, and that in the overall, the predictions of tidal truncation models are actually in line with the observations. So with this, I'll try to move to the second part of what I wanted to present today, which is how the other big process that happens as soon as you move to more massive star-forming regions. So the first one, dynamical interaction, is something that is at play in massive star-forming regions, or in the majority of the star-forming environments in the galaxy. But it's something that we can study, as I shown in our backyard in Taurus, where we can look at multiple stellar systems and see this impact. On the other hand, the external photoevaporation process is something that we really have to go and study in more massive regions. And this is actually conceptually also important to note that in these massive star-forming regions, we're actually going to see on the properties of disks mainly the effect of external photoevaporation rather than dynamical truncation. And this is something that was shown again in another nice work of Andrew Winter a few years ago, where he showed with colleagues that if you take typical star-forming regions and you take their typical stellar density and ionization field strength, you actually see that the impact of external photoevaporation is more pronounced than the one of dynamical interactions in many of these systems.
Carlo, we have a question from Thomas.
Yes, please.
He asks, oh, sorry, this is the question for the end. I should read better. Please proceed.
Okay. Yeah, so I see there are other questions, but I assume if you don't interrupt, I go on. And so this, okay. So in order to actually study, so what is also one of the reasons, in my opinion, why it's relevant to us actually start to look at this process of external photoevaporation? Because there is, as we might know, quite some evidence that suggests that the solar system actually formed in a denser and more massive environment than the one we are actually probing with many other surveys with ALMA and other instruments. And this is the environment where regions like NGC 2024, the Orion Nebula Cluster, and other objects and other systems are actually there. Yeah. So that's why we actually started to look with ALMA and with other instruments at some of these regions. So many of these regions are actually in the Orion star-forming complex, and this is a very nice image of the Flame Nebula NGC 2024, which is located really on the belt of Orion, and this is supposed to be a very young star-forming region, a very young cluster, especially because of the very high disk fraction, but also for the fact that it's highly embedded. So we actually targeted this with ALMA, following previous surveys with SMA. And we actually were surprised to find a not so easy to understand result, which is the fact that we actually seen more or less two populations in two different parts of the cluster. So on the east side, the disk masses that we measured were more or less in line with some of the younger Staphylomeria regions, at least the young and bright Staphylomeria region like lupus, not the young but fainter ophiuchus region. So this region looked very much like a very young Staphylomeria region. On the opposite, there is another population on the western side of the cluster, where the disk masses seem to be smaller than most of the young Staphylomeria regions, even the older ones, and actually more in line with the quite old upper Scorpius Staphylomeria region. And the explanation here could be a combination of actually age gradient in this region and the fact that a part of the population, the one on the east side, could be a little bit shielded from the massive stars in the region by the fact that there is still a dense ridge that is partly mitigating also the effect of external photoevaporation. Whereas the rest of the population, which could be older, is actually directly exposed to this massive star and is rapidly dispersing. So this is definitely a more complex region than we thought before, but it's already showing how much these kind of massive environments can actually change the evolution of disks with respect to what we know in our neighborhood. So we also looked at other Staphylomeria regions, other parts of the Orion complex. So we looked at the Lambda o-Ori region. So the work before was led by Sirk van der Zwiska with Rita Mann and others. And here this is work done by Megan Ansdale, Jonathan Williams, and other colleagues. And we actually targeted this Lambda o-Ori region for a number of reasons. One is that it's a little bit older than many of the other regions we looked at. And the other one is that we were interested in seeing whether the fact that there is potential suggestions that a supernova exploded at the center of this cluster could have an impact of the evolution of disks. And the disks that we detected are actually also in this case quite old, quite faint as the upper Scorpius, as the disks in the upper Scorpius region, which on the one hand is reasonable given the age of the region, and could also be due to the fact that maybe a supernova had an impact on the evolution of disks. But as soon as we looked at how the mass of the disks depends on the projected separation from where the supernova is supposed to have blown, we actually see that there is no significant effect of the distance from the supernova. So this is again something that must be explored a little bit more, since this might be due to the fact that the supernova could actually have little effect on the evolution of disks, or that there are actually disks before and after have actually moved to the cluster quite a long time. So this is quite an old region. So we might have a little bit mitigated the effects of the supernova. But this is anyway, again, interesting to see that that in these star-forming regions, you actually start to see that the disks can become, very, very faint quite rapidly, since the age of upper sky is still uncertain. They could be quite older than 5 megayear, and this really intrigued us to also explore other regions, like the Sigma Orionis region, which is again an intermediate mass region between NGC 2024, the ONC, and Lambda o-Ori, and is a region where there is an O star, so we know that external photoevaporation should be at place. This is a region where that was studied already quite some years ago with ALMA, again by Megan and Jonathan. And what we have seen there is that in that case, there is some kind of difference in the typical disk masses that are the disk mass that is observed as soon as you move away from sigma Ori, the more massive star in the region. So the more massive disks are actually located further away from this star. And we actually interpreted this in 2017 as a clear sign, as a possible sign of external photoevaporation. And we actually tried to follow this up with a very different method, which is a method that I really like because my main expertise is spectroscopy. And what I like to do in my days is to actually measure the mass-accretion rates on the star. So the amount of material that is accreted from the disk onto the star. And what we have shown with several smart colleagues in the last years is that if you measure for a population of stars the mass-accretion rate onto the central star and the total mass of the disk, which we usually assume to be 100 times the dust masses, you can expect very different behaviors on this plot depending of what is the driver of the evolution of disks. So if disks are evolving with a simple alpha disk model, so a viscous model, you expect a very tight correlation after a few mega years. So as soon as you are at ages longer than a few times the viscous timescale, then you would expect a very tight correlation between these two quantities. Whereas other processes, like processes internal to the disk, like plane formation or internal photoevaporation, or processes external to the disk, from like external photoevaporation or tidal truncation, this would actually change the position of disks on this plane. With external photoevaporation in particular, removing disk mass before the mass accretion rate is decreased. So with this picture in mind, we actually thought, why not go into sigma Orionis, where ALMA is showing us that there is evidence for external photoevaporation, and try to see whether the mass accretion rates in this region are higher than what we would expect for a viscously evolving system at 3 to 5 mega years, so a little bit below this white shaded region. So we actually did this experiment, and I show here two different plots. So on the left-hand side, I show this mass accretion versus disk mass relation for all the star forming regions we studied so far with this method. So Lupus, Chameleon 1, and Upper Scorpius, where you already see that there is quite some spread in this relation. So there is no simple explanation as alpha disk model for this kind of observations. And we already saw there that for upper score in particular, there were some issues. But on the right-hand side, you actually see this same plot that was done by Giulio Bettoni a few days ago, where he actually showed, is actually showing that when you measure the mass accretion rate from X-Shooter spectra and you combine these with dust masses from ALMA, you actually see that in the majority of the systems in the sigma Orionis region, the mass accretion rate are quite higher than what you would expect for a purely viscous evolution disk, viscously evolving disk at 3 to 5 mega years. And when you put this together, so this is the same plot that you have on the left-hand side, but with sigma Orionis now with the nice cyan dots, you see that it doesn't look, I would say it doesn't look any different than other star forming regions. And if you assume that this is older than the majority of the systems that you see here, you actually see that this might be the effect of external photoevaporation. So this is very much work in progress. And what we are actually also doing at the same time is to actually find other indirect evidence of external photoevaporation, in particular looking at forbidden lines, and to see whether the disks with the highest mass accretion rates are actually those that are externally photoevaporated. So I'll see, please keep an eye on this. We will soon we will soon let you know what we find. And I also want to mention on this aspect that two recent works by Andrew Selleck and Kathy Clark and other colleagues are actually showing that some of the effects that we see on these plots are due to the evolution of dust rather than the mechanism driving the evolution of disks. So we'll have to consider these very carefully when we finish the analysis of this work, of this data.
This time we do have a clarifying question. Neil Turner asks, what do the circles around some of the points mean on the left panel?
Yeah, those are transition disks with resolved cavities.
All right, thank you.
You're welcome. Thank you for your question. So let me just move to to the very few slides, to the final slides. So this is what intrigued Serena, and I'm sorry, I will only have a few slides on this part, but this is definitely something that it's currently very exciting for me, but also quite complicated and still very much work in progress. So what you actually want to do if you want to understand external photoevaporation in disks is that you actually want to look at the objects that are clearly externally photoevaporated. And the most clear example we have are the proplyds. And we all know that proplyds are these very nice systems, clearly known from in the Orion Nebula Cluster, observed with HST in a number of different filters, and actually iconic for Hubble. So these objects were observed also with the MUSE instrument already in the science communication. So MUSE is an instrument on the Very Large Telescope, on this one, on UT4. This is an integral field spectrograph that is covering the blue part of the spectrum. And a few years ago, this instrument was coupled with a very efficient adaptive optics system that allowed us to actually move from these images taken just with with the single limited instrument to an easy task. And all of you who studied probably know that this is not straightforward, because we're going in regimes of densities and temperatures that are not easy to test and to model as well. So we're trying to use a variety of line ratios to actually try to determine the density of these systems. And so in order to do that, we have to assume a temperature or vice versa, because there are degeneracies. But if we take the density that we derive for these two systems and we measure their ionization front size, which is done again with this data at the same precision as with HST, we can actually derive mass loss rates that are very much in line with previous results, for example, Penny and other colleagues a few years ago. So this is something very much work in progress, but in my opinion, this is really a new way that current instrumentation is giving us to actually test our model of external photoevaporation in a variety of objects. So with this, I will close, and I will just give you two take-home points of what I've said today. That I think I convinced you that we can, by measuring the size of disks in multiple stellar systems, we have seen that both the dust and the gas radii are smaller in multiple systems, and this ratio between the gas and dust radii is different, is larger actually in multiple stellar systems. And then we are starting to study photoevaporating disks with a variety of methods, ranging from ALMA to a combination of ALMA with measurement of accretion rates, for example, with a shooter, and finally with MUSE, which is actually giving us a new view of these photoevaporating disks. That was it from my side.
All right. Thank you so much, Carlo. So people want to know, for your beautiful MUSE data, what is the resolution and how does it compare to, let's say, HST?
So the spatial resolution is basically the same as HST. It depends a lot on the seeing of the night, because you can actually, this is not observations with us. It's not diffraction limited. It's actually seeing enhanced observations. So depending on the turbulence of the atmosphere on the night and the coherence time and the seeing of the night, we get down to 0.1 arcsecond or less, depending on the observations. So in these observations here, we were about 0.1 arcsecond.
All right. Great. So now we open it up to questions. I know there have been a few in the chat. Caitlin, did you want to ask your question first?
Sure. Thanks for this really, really exciting talk. But while you have that, I have one quick question on this slide still following up on what Camper said. What's the scale, sort of an AU of these little squares?
So let me
like a
see.
400 AU or
so
something?
the one you have up here is, what was that? That's a stupid thing of apple pie. I couldn't put it in the 4. I guess that was 10 AU or something like that. No, not sure. I'll check it.
Okay, I looked like on that other from that other plot. I mean, given the typical distance of Orion, maybe it is, yeah, like 500 AU or a little less. But I was just wondering, what, because the proplyds are often very different sizes in different regions. So
yeah, so these are quite large, of course.
Yeah.
I mean, to start with, I prefer to target the big ones. Yeah, as soon as you go to the small ones, the images are not so beautiful, of course.
Yeah.
But these are hundreds of AUs in size, each of these proplyds.
Great. So my actual questions, I have sort of one comment for discussion and then another question. So maybe I'll start with a comment because I know other people maybe wanted to discuss, and then I'll come back to the other question. So the first one is regarding your discussion of the Winter et al. 2020 results. And then I guess there was a follow-up by Steve Longmore and collaborators. And then very recently, there was another work that sort of disputed the explanation for the dichotomy observed in this work. I don't know if you're familiar with, if you saw Alex Mostel's recent paper in 2021.
I think I've seen it, but I'm confess I didn't read it.
Okay, so no. So yeah, so it was a really nice result to see, because when I first saw these results, I was really, really intrigued, but also surprised, because going back kind of to the second part of your talk, when you talk about binarity, we haven't observed these strong differences in binaries at sort of typical scales of planetary systems between regions of high stellar density and low stellar density. And what Alex Mostel showed is that the distinction that's observed here and in the Longmore paper in phase space density doesn't actually correspond to a difference in stellar density. And that what's driving this distinction is the velocity dispersion differences between two populations. And I think sort of the explanation of that velocity dispersion difference is actually basically age and distribution within the disk. So that the things that they're identifying as dense in phase space are actually younger thin disk stars, and I think the opposite is the older thick disk stars. And so the absence of the hot Jupiters is more a function of age. So that while obviously there's a lot of ways in which multiplicity and photoevaporation could impact planet formation, this data set probably doesn't seem to be indicating that it's dynamical in origin.
Yep. Thanks.
All right. And then we have a question from Thomas Hayworth in the chat, who says, have you ever looked at the spectral indices of the primary secondaries in the binaries? I'm just thinking of the large difference we found in the primary and secondary in HD 144668, Panic et al. 2021.
So hi, Tom. No, I didn't look at this yet. Also because we only have one band. Unfortunately, we did both observations in band 6. So yeah, I didn't really look at it yet.
All right. Next question is from Joe Najita.
Hi, Carlo.
Hi.
Thank you for the wonderful talk. That's many lovely, impressive results on a wide range of topics. So thanks so much. I had I found it really interesting, the conclusion you were drawing about the potential difference in how solids migrate in binaries versus single stars. So this is going back to the first part of your talk. And one of the facts that you used, this plot here, was comparing the lupus singles versus the torus binaries. I wonder if it'd be interesting to compare the torus binaries against the torus singles, because I think the torus singles have a higher gas to dust size ratio than the lupus ones. That we found that in a study I did with Ted Bergen, but just have a look and see if that makes any difference to your conclusion.
Yeah, so definitely something to consider. Yeah, I think so. Don't remember if Enrique did this comparison also between the lupus singles and the Taurus single in his survey. So we actually use the Taurus, the lupus singles because of similar technique. So both in the way the dust and the gas radii were measured. So with both with ALMA and UV modeling for the dust and cumulative flux for the gas. So this was the main reason to use these objects. But yeah, it would be definitely interesting to do this test, and we're probably going to do this since the paper is still under 3. Thanks.
Awesome. I really look forward to seeing what the result is and why there might be a difference. That sounds really intriguing. Thanks.
Yeah.
All right, Caitlin.
Thanks. So I'm really glad you're on this plot, because I had another question about this really, really exciting result. Can you say a little bit about the semi-major axis distribution in the underlying sample, and whether or not the sort of gas to dust radius or the predicted truncation radius to semi-major axis radius is consistent across that? I don't know how wide a range of binaries you're looking at here.
Yeah, so the projected separation, you see, for example, here.
Okay.
So, I mean, this UZ tau is a complicated system, so it's a tripole. So this is the separation between the two components on the west side. But typically the separation we have is about 200 to 500 AUs in our example. So it's not a very wide binaries, and it's not a super close ones.
Yeah.
So if you take, for example, the samples of Rachel Arkezon and Eric James, and they cover way larger range of separations.
Okay. Yeah, the motivation for my question is just that, we think it might be the case that different formation channels operate sort of preferentially at different parts of the semi-major axis distribution. And so first of all, I guess one might expect the eccentricity distributions at this age to be different between those two. And also, the environment in which the disks are, evolving might be different. So I was just curious. I guess, right now, maybe there's just not enough data to divide up the sample even further, but it's just really exciting.
Yeah, exactly. So at least my sample is not enough for this kind of analysis. The issue, so there are a few issues that I see. So one is that, so as soon as you move to closer binaries, that the probability to have strong interaction is very high. So what the way, measuring that, especially gas radii in systems like this OIR, is quite complicated. So studying those closer separation binaries will be complicated. Going to wider systems, so wider distances, I think that's okay from an observational point of view. The point there is what will be the effect of the truncation. So if it will be less than what usually a single system is doing. So I think also that this kind of separation is more or less what we want to study. So this said, of course, I'm trying to, now the distributed peer review should be almost over. Of course, I'm trying to get more binaries in this separation range and also in other subforming regions. And so let's see if we're going to get more ALMA data on this and to study actually what you're suggesting, which is very interesting.
Yeah, no, and I guess the only counterpoint I'd make to your concerns about the two ends is that in fact finding, if you found the typical separation at which the data becomes too hard to interpret, that in itself is very interesting because that tells you something about what's going on in the systems. And if you find the point at which it becomes a boring echo of the single star properties. That's also really interesting. So I wish you and your ALMA proposals luck, because I hope you get more data.
Yeah, there is a high probability on these audios. There are at least 3 or 4 people reading my proposal, so it's fine.
Well, you should give Carlo.
Oh, it's anonymous. Sorry, so I should not say it.
I'm not one of them, unfortunately.
Let just all the binary system, the binary proposal pass, so I'm fine.
All right, Serena.
Yeah, I just curious about how long do you have to expose for those 2 targets? The fantastic.
So thank you all, and I would like to invite you to unmute Carlo for a beautiful talk. Thank you, Carlo.
Thank you.
Hey, Camber.
Mm-hmm.
In August.